Assalamualaikum warahmatullahi wabarakatuh. I bid to Dr. Abdul Halim. I'm Mohammad bin Zulkifli from UTP, and in this presentation, I will answer the question 1B in the extended experiment of seismic wave imaging. Start off with the seismic wave incoherency. So, coherence is defined as a measure of similarity between the waveform or trace, while the incoherency is known as the horizontal spatial sharing of both horizontal and vertical ground. So there is two sources of incoherency that we can see. The first one is the local wave scattering. This is due to the spatial variation from scattering of wave caused by the heterogeneous nature of soil or rock along the propagation path of the incident wave field. Next, we have the wave passage effect. So wave passage effect is the systematic spatial variation due to different in arrival time of seismic wave across a foundation due to inclined wave. Here we have two figures. So this figure shows the seismic data, and in the seismic data, we can find the incoherency. There is a fault structure that can be represented from the red line, and there is also the gas cloud which can be represented in the red circle. So in this gas cloud we can see the truncation of amplitude and the frequency, and then we can also see the accurate depth of the gas cloud area. Therefore, to solve the problem that was identified earlier, a method was proposed here. The method is the illumination factor analysis. So illumination factor analysis is a combination of focal beam analysis and a ray tracing method. So this illumination factor analysis allow for a higher level of confidence during survey design validation. And then it help in illumination of target surface reflector, and which in this case is the cloud zone. Let's first look at the focal beam analysis. So focal beam analysis are able to give information for specific target zone. However, illumination analysis of other locations around the target is relatively unknown. And then focal beam analysis propagate a unit wave outward from the target reflector until a signal reach the surface level. And this wave is in form of monochrome frequency and continue information from a single point. Therefore, to cover the whole reflector, a continuous simulation was run for the whole inline of a single cross line within the depth reflector. And on the target surface, the focal beam analysis will be carried out as the spatial domain. And this spatial domain analysis that was carried out, which result in the resolution function in order to have a true surface amplitude. Next is the ray tracing method. So ray tracing method is based on the number of ray hit on the reflector. The inability of ray to incorporate a true amplitude information during illumination analysis can be a disadvantage of this method. So how this method works is the multiple ray fan were interpolated toward the reflector and then reflected back, and the number of rays detected at the relevant location were recorded and analyzed. Now is the methodology in order to combine both focal beam analysis and the ray tracing method. So at the start, we will have a comprehensive velocity model that was built using the field velocity information, and begin at the reflected depth of interest. A wave is sent toward the surface level where the source and receiver are placed. The outgoing wave is then convolved with source and receiver position before being propagated back toward the target reflector. And then the ray tracing analysis was conducted by using the same acquisition setup after finishing the focal beam analysis. For multiple source position on the surface, a fan ray will be shot towards the target depth reflector, and the ray will travel through the layer and anomalies and will only reflect back toward the surface once it reaches the depth target and obey certain rule. So the reflected ray detected back at the surface level, and the only ray that will be used for ray hit count. Then using both numerical solution obtained from separated method, we will use a mathematical manipulation to calculate the illumination factor, and the outcome from this factor will be used as the basis for new illumination analysis. This methodology is further summarized in the figure there. So other than the illumination factor analysis, here is the second method that was proposed in order to solve the incoherency that was found before, which is the Q migration. So this Q migration is best for spatial variation in absorption properties and frequency dependent dissipation effects. It can also used to improve amplitude and frequency loss for structure and detect poor event continuity. And then accumulation is applied to estimate absorption model from frequency dependent Q tomography to compensate for Q effect relative to the background. And this goes beyond simplistic surface consistent assumption to compensate for transmission effect anywhere in the overburden. It also implement for curse off beam and RTM algorithm. In conclusion, there was two proposed techniques in order to solve the incoherency that was found in the seismic data, which is the gas cloud effect and the fault structure. The first one we have is the illumination factor analysis that combine focal beam analysis and the ray tracing method. And the second proposed method is the Q migration. With that, I think this is the end of my presentation. Thank you.